All right, welcome to Earth Science, everybody. Time for part 3 of the Absorption and Radiation Lab. So if you have not done parts 1 and 2, please make sure you go back and do that first. What we've got going is a similar idea to what you did in parts 1 and 2. I'm going to take the lamp, which you can see is off-centered now, put it in front of 2 beakers, heat them up, and for 15 minutes, we'll read the temperatures as they go up, and then let them cool off for 15 minutes. The trick is going to be that for the first part, these two are going to be exactly the same. For the second part, for the cooling part, what I'm going to do is take this larger beaker and put it over the top like that. So I would say that we'd expect them to heat up roughly the same. You know, little differences might show up, but the cool off part is what we're going to watch for something different to happen with this. So in terms of, this is always slightly confusing. It's not a huge deal that I called them covered and uncovered for both parts. It's not covered at the beginning. So maybe we can say soon here. Doesn't really matter. You don't have to write that in there if you don't want. You'll get the points. All right. So I already looked at the temperatures. They're both 18 to start. So if you want to put, this is going to be just like the other one. So I'll do the first one. And you guys are on the hook for the rest. All right. And those are in degrees Celsius. We will start a timer that I did not get out. Good job. We will start a timer and start the lamp here in just a moment. All right, and we're off. So what I'm going to do also now is talk about the front page. I'm going to do the same thing where we're just doing every 5 minutes. So I have a couple minutes. We'll come back and we'll see what's going on up here. So let's start filling out the front page. These are going to be oversimplified definitions as per usual with me. You guys should be used to that by now. So the absorption phase of all of this lab is when heat energy is gained. And that's kind of the big thing. By the objects, whatever the beaker was or can was, whatever it might have been, and radiation. And this is the part where it's like, again, this lab is obvious because you know that if you put a heat lamp on something, it's going to warm up, and if you take it away, it's going to cool off. You guys already knew that, but we have to start seeing it as these two processes discretely, because when it comes to figuring out meteorology, energy from the sun interacting with our planet and our atmosphere, it's critical. So this is going to be when heat energy is given off the objects. How about that? All right. So easy enough, right? Heating, cooling. But let's just see that cooling is giving energy away. When it heats, the visible energy that heats Earth's surface has a shorter wavelength. So what I'm going to do over here is pop over to your Earth Science reference tables and shrink my head down a little bit. Energy that's coming into our planet is going to be, like, clearly there's visible light because you can see when the sun's out, right? But also over on this ultraviolet side. Now think about that. You've seen sunglasses with ultraviolet protection, sunblock, ultraviolet protection. We're always talking about that, right? So the energy coming from the sun has a lot of these UV rays. And if you're getting how to use this electromagnetic spectrum, we've just only kind of peeked at it a little bit, and we'll keep on slowly introducing it. This is from your reference tables, page 14, by the way. Ultraviolet is on the shorter wavelength end. So this energy is coming at us from the sun with a shorter wavelength. Now, the trick is the energy is transferred back to the atmosphere. Once something heats, these two beakers are heating up with that sand, right? When it starts to cool off, when it gives its energy back, it doesn't do it at that same wavelength. Otherwise, you know, it's a longer wavelength, which is a tricky thing to like see. I have an infrared camera at school, but we're not at school. It tends to give off these infrared rays. Have you ever heard of infrared cameras? You know, rescue helicopters have them because they can see like the heat energy that a body gives off in the middle of the woods, something like that. That's on this longer wavelength. Okay. This is the reason why your car also gets hot in a parking lot in the summer. The sun has no problem getting through your windows, right? And if it were just to hit something shiny, like hit that little part of your seatbelt and go bouncing right off, it would go just as easily right back through your windows. So why does it actually get hot in there? It's because the seats, all the interior stuff heats in that sunlight. And then when it gives off more energy because it's getting hotter, it gives it off at a longer wavelength. And that longer wavelength doesn't escape the glass of the car. So this longer wavelength energy, which is just infrared again, similarly doesn't escape the atmosphere. The atmosphere does a good job of hanging on to that energy, not letting it go. And it's called the greenhouse effect. It's just like a greenhouse. Greenhouse effect. I'll make this bigger. Somebody said they couldn't really see this on the computer. Okay. So it comes in at a shorter, but when something's warm, it gives off infrared energy, which is longer wavelength, which does not escape the glass of a greenhouse, does not escape the glass of your car in the parking lot, and does not escape our atmosphere. Our atmosphere holds on to that infrared energy a lot more efficiently than it does the shorter wavelength energy that is coming in and hitting the planet. Now, this is a good thing. We're very happy that we have a greenhouse effect because it keeps our temperatures kind of balanced. What I'm going to have to do real quick is switch over to our 5-minute reading. In fact, you know what I'm going to do? I'm just going to write it down so I don't interrupt us too bad. We're at... Okay. All right, so we're happy with this greenhouse effect. We really like this here on Earth. If we didn't have it, so let's look at something else nearby that doesn't have an atmosphere that probably gets an equal amount of sunlight, which is the moon. If we had no atmosphere like the moon does, what we see on the moon is that it goes from about negative 280 degrees at night. And granted, their nights are like a week long, maybe a couple weeks long. But nonetheless, and up to 260 degrees. These are in degrees Fahrenheit during the day. So that's a swing of over 500 degrees. You know, people around here complain when it goes down by like 20 degrees at night. If it went down 500 degrees at night because the greenhouse effect wasn't a thing, we wouldn't be alive, let alone able to complain, right? So we really, really, really rely on this greenhouse effect to keep the dark side of the Earth from plummeting down and being extremely, extremely, extremely cold. All right? We like it. Don't associate it with bad. When we start talking about climate change and global warming, the greenhouse effect is a necessary thing. We need it. But too much of a good thing can be bad. There is a runaway greenhouse effect because of a ridiculous amount of carbon dioxide in the atmosphere on... that was weird. On Venus. How does it want me to spell check? Did I mess up my spelling? Capitalize. The temperature there, you can melt lead right on the surface, almost 900 degrees Fahrenheit. In fact, so it's the hottest planet, but it's not even the one that's closest to the sun. It's the second one out. And it's because of this greenhouse effect being so strong. So too many greenhouse gases. Now, we'll talk about these a lot. But I'll tell you right now, if you're the type that can just memorize quickly, the greenhouse gases that we have to have in our noggin to make it through these tests: methane and carbon dioxide. Methane and carbon dioxide are very strong greenhouse gases. In fact, methane is about 4 times stronger. Carbon dioxide is the one we're worried about because we're unlocking a lot of it from the planets and putting it into the atmosphere. Methane's a big one, though, too. All right. So that's going to be the purpose of this part 3, is to see, once I cover it up, as these 2 sand beakers are cooling off, will this larger beaker create a little mini greenhouse effect? Will it not allow as much to escape? Okay. Sorry, my son's trying to be as noisy as he can with a bag of chips over there. All right, what we should see with our data, this goes for all the labs. And it's a bigger science rule. A good absorber is also a good radiator. Something that efficiently heats up also is going to efficiently cool down. So the things you saw go up the most should also be the things that went down the most, is the lesson. So we'll see if your data matches. Hopefully, since I'm running all the labs I do, usually when students are running the labs and people are touching and poking and prodding and not paying attention, there's some ones that don't work out. But in general, this lab tends to work pretty well. All right. So that's all the theory behind it. I skipped the 5-minute reading here because I was babbling, but I'll plug it in because we've gone a little past it. So at 5 minutes, the soon-to-be covered one was at 20 degrees Celsius, and the other one was at 19. Heating up a little bit differently, but that's okay. That happens. All right. And that's going to get us almost to our 10 here. So rather than press pause, let's just keep going. All right, I paused anyway to get us there. We are both at 23 degrees Celsius. At 10 minutes, we're both at 23 degrees Celsius. I'll pause and come back at 15. All right, we're back for the 15-minute reading. And remember, now's the part where we really start the greenhouse effect part, where we got these warm uniformly. They're going to be pretty close. And then we'll put this over one of them to go. So here we go now. Yep, they're close. We both made it to 27. So 15 minutes, 27 for both of them. And now what we'll do, turn off the lamp, get it out of the way because it's still hot. Cover this one up. So now we're going to let this one be the covered beaker. Let it cool off slowly, or hopefully, ideally, that'll create a bit of a greenhouse effect. So as this one gives off infrared energy, it gets trapped in there, and therefore the whole thing doesn't cool off as much. This one's free to give off its energy without an atmosphere. So think of it like Earth on that one, Moon on that one. We'll come back and see where we're at. There's the noisemaker. Goodbye, noisemaker. We'll be back. All right, so we're back for the 20-minute reading. I'm seeing for the covered one, 26, and the uncovered one, 25. 26 for covered, 25 for uncovered. That was at 20 minutes. We'll be back for 2 more. All right, 25-minute reading. We are at 25 for the covered and 23 for the uncovered. I think it's working. We'll be back for one more. All right, so we're finally done, and it looks like it works pretty well. This one's higher. The covered is at 24, and the uncovered is at about 19. So looks like it showed us what we were looking to show. That'll be great. What else? Rate of change problems I went through pretty well in video number 1. If you forget how to do these, go back to Absorption Radiation Part 1. It'll explain all those. This is kind of, I'm not going to worry about this as much. I'll give you the answer here. This is a hard one. If you've done, in math class, if you've calculated slope, rate of change and slope graphically are kind of an identical concept because it's how quickly is it dropping off or how quickly is it going up. That's kind of abstract, though. I usually, in a regular year, maybe beat on that a little bit more. So what show the greatest rate of change? Really just go up above here and look at for the highest number out of those problems you just did. All right, let's talk about specific heat quick. Specific heat is how much energy does it take, and joules is a unit of energy. How much energy does it take to heat 1 gram of a substance by 1 degree Celsius? Which, I know I'm throwing a lot at you with that sentence, but water, liquid water, would take 4.18 joules of energy. Joules is just a unit of energy, so about 4 energies to heat a gram of water by a degree Celsius. If you notice, all the other ones are a lot lower. And sand's not on here, but sand is made of some of this other stuff, right? So sand has a lower specific heats. That means it takes less energy to get it to heat up. So when we did our experiment up there in part 1, what we should have seen with sand having a lower specific heat is that it takes less energy for it to heat up. So therefore, given an equal amount of energy between the sand and the sand should heat up the most and cool off the most. Water takes 4 energies to heat up. Sand takes maybe 1 to less than 1. So did the water heat up a lot slower because of that? That's what specific heat is going to show us. So water has a very high specific heat, and that means it takes like a lot of energy to get it to heat up. Okay. So that's going to help you with that question there. That question there. That's from the reference table, what we just did in part 3 with the energy leaving. Look to the top of the lab if you did, to those notes we did. Yeah, I'm thinking all of these are doable based on the videos we did. All right, short versus longer wavelength, match them up. And should you need it, this specific heat table is on page 1 of their science reference tables as well. If this will go quickly. All right, that's a mess. I won't make you sit through this thing fumbling around. But that should do it. Thanks for sticking through all these absorption radiation labs. Good job. This is the end. We're going to say goodbye now. You want to say goodbye?
Goodbye.
No, don't close it. I got to hit the button here. Thanks, guys. We'll catch you soon.